So for this recording, we're going to work on chapter 2, and in preparation for lecture exam 1, which is on September 8th, Monday, September 8th, we want to know chapter 2 up to a certain cutoff point. So let me go ahead and show you where that's going to be. And so for lecture 1 exam, we're going to have 50 questions, multiple choice. You're going to want to know all of chapter 1. And for chapter 2, your cutoff point is going to be somewhere around slide 31 here. So 30-ish, you could probably stop there if you wanted to. 31, it starts to talk about the next subject that it gets into, which is macromolecules. And then by the time you get to 32, it starts talking about the first type of macromolecule we'll discuss. So this particular portion of chapter 2, we're going to do later. So we'll probably try to squeeze it in as we're going over chapter 4, metabolism, and we might ask a few questions about macromolecules at that time. But for our lecture 1 exam, let me again go back to modules. Here's week 1. We went over chapter 1. Week 2, I'll be here Monday, but I will be gone, and this is probably when you start watching this video, Wednesday and Friday. We don't have class the following Monday because of Labor Day. I will also be gone the following Wednesday, and then I'll be back this Friday, and I will review for our first exam. So lecture 1 exam, again, falls on Monday, September 8th, and it's going to include all of chapter 1, and it's going to include chapter 2 up to about slide 30. So you can kind of cut off when it starts talking about macromolecules. So for our recording today, we want to keep it as short as possible so there's not a lot of confusion. Again, I'll be able to answer any questions that you have when I get back that Friday before the test. But a lot of chemistry that we need to understand in anatomy physiology is really just based off definitions. Like, for example, what is an atomic number? What's an atomic weight? What are the atoms composed of? To a degree, what's the difference between atoms and elements? So oftentimes, as I'm going over some of these different types of definitions and how we're going to recognize them and how we're going to describe them, I'll probably be going back and forth between this page and this page, the periodic table of elements, because a lot of times this has a lot of the information on it that's mentioned here. It's just kind of written in code. So I'll tell you how we can interpret this and what's being shown on here. But ultimately, we don't need to be chemists to understand anatomy and physiology. We just need to understand some of the basic components. So the whole point of learning chemistry to begin with in this class is because a lot of physiology is based off ideas that are discussed in chemistry, particularly ions. For example, when we talk about ions, ions are things that have gained or lost electrons. So what are electrons? Electrons are subatomic particles that make up atoms. So we'll talk about why do we gain electrons sometimes? Why do we lose electrons sometimes? I'll even give you some examples of why it works. But again, that's going to end up leading us into further discussions about physiology and metabolism later. So we just need to learn the basics. So some of the most basic things we do, let me show you where I am in the PowerPoint. Here's slide 1, slide 2, just talks about general idea about chemistry. Slide 3, here's slide 4, which is the periodic table. I'll talk about this. I'll probably come back to this slide quite a bit, at least to grab some numbers off of it. Here, this is the first slide we're going to kind of get into, where we start talking about different definitions. It starts talking about things like, atoms. What are atoms? Atoms are the simplest individual unit of an element made up of protons, neutrons, and electrons. So let's dive into that first. And one thing that you're going to notice that I'm going to do is I'm going to go back and forth between the screen and a piece of paper that I'm going to draw on. So when I stop sharing screen with you, it's going to go to my document projector, and we're going to kind of draw out some things here. So when you're dealing with atoms, atoms are made up of smaller things called subatomic particles. And the subatomic particles you're all familiar with. Those are things like protons, which are going to be found in the nucleus and carry a positive charge. You have things called neutrons, which are also going to be found in the nucleus. They're neutrally charged. There's no charge to a neutron. And then you have electrons, which orbit around the nucleus, and those are the ones that are negative. So when you're looking at atoms, oftentimes pictures in books of atoms are drawn in what's called a Bohr model or a Bohr diagram, in which it ends up putting the protons and the neutrons in the center, which that's pretty accurate. So imagine we have like a little proton right here. Here's a neutron. Here's another proton. Here's a neutron, something along those lines. That ends up making the core or the nucleus of the atom, where the protons themselves are positively charged. The neutrons don't carry a charge. And then orbiting around that in what's called shells or orbitals, that's where the electrons would kind of go. So if I had something like this, maybe it would look like that. So again, protons and neutrons are found in the nucleus. Protons are positively charged subatomic particles. The neutrons carry no charge. And then the electrons will orbit around the nucleus in what's called shells or orbitals. And when you show it or you diagram it in this way, it's called a Bohr model or a Bohr diagram. So let me give you an example of one. So this is where I end up going back and forth to the periodic table. If we end up looking at something like, say, lithium. Lithium's pretty similar to what I just drew. You'll end up seeing what's called the elemental symbol. You end up seeing what's called the atomic number, which represents the number of protons in the atom. And you end up seeing what's called the atomic weight, or if you're talking about an individual atom, it might be called an atomic mass, okay, or atomic mass unit. So you have the elemental symbol, the atomic number, the atomic mass. So I'm going to write that down on a sheet of paper real quick, and then I'm going to, again, switch screens, but let me go ahead and write it down while I have it in front of me. At one time, I was supposed to memorize this periodic table, and for some reason that just didn't stick. So let me draw one lithium atom for you. So based off the information I've been given on the periodic table, again, this is the elemental symbol for lithium. It's not always going to be the first two letters. Sometimes you'll see things that are abbreviated like this on the periodic table, and that actually stands for sodium. Sometimes you'll see something like this on the periodic table, and that actually stands for potassium. So it's not always the first two letters of the word that we use currently. Sometimes it'll be a letter or the first two letters of an old word that used to represent the word that we use now. Like sodium used to be called natrium or natron. Potassium used to be called kalium. Sometimes when you see iron, like iron, you might sometimes hear about as ferrous or ferrite, right? So again, the elemental symbol does represent what we're talking about, but sometimes the letters that are used on the periodic table don't exactly sound like the word we use currently. But lithium's an easy one. Lithium's Li. And underneath that, you see what's called the atomic number. And you see the atomic mass or the atomic weight. So what the atomic number is going to tell me specifically is the number of protons that are in an atom. So atomic number always equals the number of protons that are in an atom. So with lithium, we certainly have 3 protons. So I'll just draw 1, 2, 3 little protons right there. While the atomic weight gives me the number of protons plus the number of neutrons. So I'm just putting WGHT as weight, and that equals protons plus neutrons. I'm just going to put P plus N. So what I'll do, this was 6.94, is I'll just go ahead and round up to the nearest whole number, because it's not like we have 0.94 neutrons, it's just an average. But let's just go ahead and say 7 is my atomic weight. And if I knew that atomic weight was protons plus neutrons, and I knew in lithium my proton number was already 3 plus blank equals 7, then that meant whatever's left over must be the neutron number, so it must be 4. So we had 3 protons. We'll have 1, 2, 3, 4 neutrons. That's what the nucleus of lithium would look like. And then I can surround that with these little shells or orbitals. And I'm going to put 1, 2, 3 little electrons right there too. So I'll show you where that came from in just a second. But lithium would look something like this. Again, if the lithium elemental symbol Li has the atomic number of 3. That tells me I have 1, 2, 3 protons. If the atomic weight, let's just go ahead and say is 7, that means we have 4 neutrons because 3 plus 4 equals 7. Right? Or you could say 7 minus 3 equals what? Whatever's left over is the neutron number. And then one thing that's kind of hidden in this information is this symbol for lithium is not showing a plus or a minus beside it. So what that implies on the periodic table is you're dealing with neutrally charged atoms, ones that don't have a positive charge to it or ones that don't have a negative charge to it. So what that means is the number of positively charged subatomic particles and the number of negatively charged subatomic particles must be the same. In simpler words, that means that your electron is also 3. Your electron number is also 3. So the atomic number specifically gives me the number of protons, but it also secretly gives me the number of electrons as well. So when I put the electrons around there, I'm going to put 3 electrons around there. So I'm just going to put these things in shells or orbitals. And there's a little rule I'm following that tells me how many shells I have and how many electrons go into each shell. But we'll talk about that in a little bit, right? That's called electron arrangement, or the octet rule that tells me how that works. But that's what one lithium atom would look like. And every lithium atom kind of looks like that, unless it's an ion. You know, if I ever have like a lithium ion, like your lithium ion battery, it's lost one of these electrons. And you'll be able to recognize that it's a lithium ion because it'll now be called Li+. Okay. So we'll discuss that in just a minute. But again, when I'm looking at some of the basic definitions of an atom is the simplest individual unit of an element made up of protons, neutrons, and electrons. The protons and neutrons are found in the nucleus, with the protons being positively charged subatomic particles. Neutrons have no charge, or they're neutrally charged. And then the electrons are found orbiting around the nucleus in shells or orbitals, and they are negatively charged. So again, here's some examples of what's called a Bohr model. Okay. Elements, again, fundamental substances of matter. So these are like the ingredients that make up the universe. The atoms are the individual pieces of those ingredients. So what kind of puts an atom as part of an element is the atomic number. So you can imagine that if I am trying to pick teams, the way the element knows which atom belongs to its team is just by looking at its atomic number. So for example, if I go back to the periodic table, every atom that has 21 protons is scandium. Every atom that has 13 protons is aluminum. It belongs to the aluminum category, or the aluminum element. If I'm an atom that has 7 protons, then I belong to the element nitrogen. Okay. So if I were to take a sample of pure nitrogen, every individual atom in there, if I could count them by hand, it would have 7 protons in its nucleus, every single one. Okay, that's what made that atom part of the nitrogen element. So it's the atomic number that assigns you to your proper element. Okay. Again, going back. So atoms are made up of subatomic particles. On the periodic table, sometimes they're telling us how many there are. So when you look at the atomic number, that tells you the number of protons that are in each atom. If you look at the atomic weight, that's telling you the number of protons plus neutrons. And then secretly, the atomic number is also telling you the number of electrons, unless it has what's called ionized, gained or lost electrons. And when you look at the periodic table, none of these have ionized yet, because I don't see H plus or H minus, I just see H. So that means the number of positively charged subatomic particles and the number of negatively charged subatomic particles must be equal. So if I know I have 1 positively charged proton, I must have also had 1 negatively charged electron to equal that out. Okay. If you don't understand what I'm saying, just follow this rule. Lithium, based off the periodic table of elements, has 3 protons. It's going to have an atomic weight of about 7. So if I take 7 and I subtract 3, whatever's left over is the number of neutrons. That's 4. And we can just assume that elemental lithium would also have 3 electrons. Okay. So this is telling me the number of protons. It's also telling me the number of electrons. This is telling me the number of protons plus neutrons. If it relieves stress on the test, we're not going to have a periodic table. You're not going to have to do any math if you don't want to. But I might just say which of the following indicates number of protons: atomic number, atomic weight, and I'll give you some various other detractors. So a lot of what we're learning in chemistry right now is just its basic definitions. When you get into compounds, compounds are when you have two or more atoms of different elements coming together. So examples of that would be like carbon dioxide, in which you have a carbon atom and two oxygen atoms all joined together to form one substance. With water, H2O, you have two hydrogen atoms and one oxygen atom all joined together to form a unique new substance. With ammonia, you end up having a nitrogen atom with three hydrogen atoms all joined together to form a new substance. So these are considered compounds because you have more than one element represented, right? These also happen to be molecules because molecules, the definition here, I'm not a huge fan of. It says the smallest fundamental unit of a chemical compound that can take part in a chemical reaction. I don't like that they use the word compound there because not all molecules are necessarily compounds. So a better definition of molecules is the smallest individual piece of a known substance. I think that works better. So for example, let me show you. Water looks like this when it's joined together. You'll have a hydrogen atom joined together by an oxygen atom. These little lines are just representing chemical bonds. So in this case, shared electrons holding them together. But this is a compound, but it's also one molecule of water because a molecule is the smallest individual piece of a known substance. So if I had a glass of water right here, there's many of these floating around in there, many of these. But I can't get any smaller than that and still be water because this is not water. This is not water. Now I have water. So that's as small as water can possibly get and still be water. Therefore, that's one molecule of water. But this is also a compound because it's not just one type of element. There's more than one element present. Okay. Another example in which you have a molecule that's not a compound is like the O2 that we breathe. The oxygen we breathe is two oxygen atoms joined together. It looks like this, where you have these two oxygen atoms joined together by double bonds. That's what we breathe. So this is one molecule of oxygen, but it's not a compound, right? Similar like hydrogen gas that kind of burns, you know, if they do like hydrogen fuel cell vehicles, normally that burns hydrogen gas, and that's two hydrogen atoms joined together. It's H2. So that's one molecule of hydrogen gas that you would burn in a hydrogen fuel cell vehicle, but it's not a compound because there's not more than one element present. So hopefully that helps. Again, we don't want to dwell on these things too much because the more you discuss it, the more confusion it adds. When you get into isotope, isotopes are basically saying there's a predictable number of neutrons in any given atom of an element. And if it starts to vary from that, like let's say one atom that's part of an element has an atomic weight that we expect, and then another one ends up being a little bit heavier, that's probably an isotope. It's probably got a variable number of neutrons. So when you have an isotope, you end up having the same atomic number, but different atomic weights. So for example, I could have carbon 12, which would be the normal number we would expect. This is the most common form of carbon, but you could also have carbon 14, right? Both carbon 12 and carbon 14 have 6 protons. If not, you couldn't be carbon. But carbon 14 ended up having 8 neutrons instead of the normal 6, right? So because the neutron number changed or the neutron number varied, you ended up with a carbon isotope, right? So that's how they do carbon dating sometimes, because sometimes the isotopes become unstable. But again, without too much delving into it, what's an isotope? It's atoms with the same atomic number, but different atomic weights. Another way of saying that is the neutron number has changed from what we had expected to be. And the stuff we had expected to be is what's showing up on the periodic table, right? So most carbon atoms would have 6 protons and 6 neutrons, because when I add those together, that gives me 12. Similarly, most nitrogen atoms are going to have 7 protons. They have to be nitrogen, and they would have 7 neutrons, and that's what gives me 14. But I could have an isotope of nitrogen that has an atomic weight of 16, right? It would still have 7 protons, because you have to have 7 protons to be nitrogen. But if it had an atomic weight of 16, that means we gained 2 neutrons. So that would be an isotope of nitrogen. And one other word I want to go over with you. Let me just write it down first before we show it on the screen, because this is a word that we will run into a lot. Don't confuse the word isotope, because isotope usually means you have a change in neutron number. So it's the neutrons that have changed. Ions is a change in the electron number. So with ions, you have an atom or atoms that have gained or lost electrons. And when that happens, you end up with an atom with a charge, either positive or negative, okay? So ions are charged atoms because they have gained or lost electrons. So let me give you an example of that, again, by going back to the periodic table. And I'll show you why we can use the atomic number to help us assume how many electrons would be there if it's not an ion. So let's go back and do a simple one again. Oops, sorry, I didn't mean to click out of that. Let's go back and look at something small like beryllium. So I'm gonna write a couple of these things down just so I have them. And then I'm gonna click off this screen. So beryllium has an atomic number of 4, atomic weight of 9.01. I'm going to go ahead and write down lithium again. Lithium is 3, and I'm just going to put 7. Helium is 2 and 4. Let me put chlorine down here. Chlorine is 17 and 35. That's good enough for now. I'm not going to draw all these out. I want to use it for a reference later. Hold on, let me write down sodium as well. 11 and 20, 22.99. So I'm just going to go up to 23. So I just wanted those for a reference, so I don't have to keep going back to the periodic table. So when I look at, say, lithium versus lithium ion, normal elemental lithium, the stuff that is being demonstrated to you on the periodic table of elements, is neutral. And I know it's neutral because I don't see an Li plus and I don't see an Li minus on the periodic table. It just says Li. So if I'm drawing a lithium atom that's neutral, it's going to have 1, 2, 3 protons for sure, because that's what the atomic number officially tells me is the number of protons. So 3 protons in lithium. If I take 7 minus 3, whatever's left over is going to give me the neutron number. So that means we have 4 neutrons in lithium. And because there's no charge, I'm assuming that the 3 positive subatomic particles must be negated by 3 negatively charged subatomic particles. So there's 3 electrons in lithium. Okay. And again, I can draw this out one more time and show you in just a second. So we got 3 protons in the middle, each of which carries a positive charge. I'm going to have 1, 2, 3, 4 neutrons. I didn't mean to darken that one in so much. And then I'm going to end up having 1, 2, 3 electrons. This has a negative charge, this has a negative charge, and that has a negative charge. So the number of positive charged, 1, 2, 3, and the number of negatively charged subatomic particles, 1, 2, 3, canceled each other out. Therefore, that lithium atom has no charge. But watch this. Let me draw a lithium ion where we end up having 1, 2, 3, protons in the middle. Forget the neutrons for right now. I'm not even going to draw them. Let's not worry about it. We're only going to draw the charged particles. So you have 3 protons for sure in lithium. You have to have 3 protons or it's no longer lithium, each of which has a positive charge. So 1, 2, 3. Let's go ahead and draw the electrons. 1, 2. We had 3 to begin with because lithium starts off neutral, each of which has a negative charge. So the protons has a positive charge. So 1, 2, 3. The electrons have negative charge. So 1, 2, 3. Those would normally cancel each other out, right? But what if I got rid of that electron right there? If I got rid of that electron and it takes its negative charge with it, now I have 1, 2, 3 positively charged subatomic particles. I have 2 electrons, each of which has the negative charge. So those cancel. But because I have 1 more positively charged subatomic particle than I do negatively charged subatomic particles, that creates a positive overall charge of lithium. And now I have a lithium ion. So how did I get Li plus? Because I gave up or I lost an electron. So when you ionize or you form an ion, again, you can either gain electrons, or in this case, I lost an electron. And when you lose an electron, it takes its negative with it. So it becomes positive in nature. So when you lose an electron, you actually become a cation or a positively charged ion. If you gain an electron, though, it's going to bring its electric charge with it, right? So electron, I'm just putting negative. Sometimes an abbreviation for electron is just E negative, if that makes it easier on you. So if you lose an electron, you become positive like lithium did. But if I gain an electron, I'm going to become more negative. So for example, let me use, let's go back real quick to the periodic table. And I'm going to take one of the halides. So let me slide this down. It's on my screen in the way. If you look at fluorine and you look at neon, we're going to kind of discuss a little bit like why things ionize to begin with a little bit here. Neon happens to be a very happy atom. It doesn't need to mingle with any of the other atoms. It's completely inert. It's completely stable, you could say. So neon's very happy because of how stable it is. And the reason it's stable is it has just the right number of electrons it needs to fill up its shells optimally. So I'll draw out neon for you real quick, and then I'll tell you what rule I'm using to determine optimal, electron arrangement. So neon has an atomic number of 10. It has the atomic weight of 20.18. So I'll just round down to 20. And if we were to draw out, say, neon versus, say, fluorine, fluorine has the atomic number of 9 and it has the atomic weight of 19. So let me draw neon first. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 protons, each of which carry a positive charge. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. I'm going to draw 10 neutrons in here. They don't carry a charge or anything like that, so don't worry about that. But I'm just going to draw 10 neutrons. 2, 3, 4, 5, 6, 7, 8, 9, 10. That's my nucleus. So when you look at the atomic weight, it actually gives you the weight of the nucleus. It's the protons plus the neutrons. So we knew we had 10 protons. If I subtract 10 from 20, that tells me how many neutrons I have. So there was 10 of those. And then when I surround my nucleus with these electron shells or orbitals, I'm going to put 2 shells there. I'll explain why in just a minute. And I'm going to put 1, 2 electrons in the first shell. And then I'm going to put 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second shell. And that's what neon would look like. Just trust me. Just take my word for it. And each one of those electrons would have a negative charge attached to it. So negative, 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 negative. So that ends up giving me 10 negatives. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those all cancel out, right? And that equals neon. That's what a neon atom would look like. So Ne stays Ne, there's no plus, there's no minus, okay? And the reason Ne is never going to ionize, it's never going to gain electrons and it's never going to lose electrons, is it's going to follow something called an octet rule. And I'm going to show you where this is in the notes in just a second. It's called an octet rule, which basically tells me the number of electrons I can assign per shell or per orbital, right? And for our purposes in this class, our octet rule is going to work like this. So for our class, when we're following the octet rule, let's say we have a nucleus right here. Don't worry about what's in there. The first shell that is surrounding that nucleus can hold up to 1, 2 electrons. The second shell, here's where the octet comes from, can hold up to 8. And if it has 8, it's full and it's happy, right? So the shells are happiest when they're full. So the first shell holds up to 2. If it has 2, it's full. If I have more electrons to assign, I have to add another shell. The second shell holds up to 8. So when it has 8, it's full and it's happy. The third shell also is going to hold up to 8, and that's going to make it full and happy. And this is what's called the octet rule. So the first shell holds up to 2, second shell holds up to 8, third shell holds up to 8. And again, for our class, that's all we need to memorize because we're not worried about transitional atoms or elements. So 2, 8, 8. So when I look at neon, neon had that. If I look at neon, neon had 10 protons in the middle. It had 10 electrons surrounding the nucleus. So I had the first shell here that I added. I put 2 electrons in. So that's full now. I added 8 more in the second shell. And together that gave me 10 electrons. It had 10 protons. It has 10 electrons. They cancel each other out because we had just as many positive charges as we had negative charges. And we don't need to gain or lose any electrons here because that shell is full. And when you look at the outermost shell, we sometimes call this thing a valence shell. That's the one that we're concerned about being happy and full, right? Because if your valence shell hasn't fulfilled its octet, or if it's not full, it's not happy, and we're going to have to make some changes. But with neon, everything worked out. So neon is what we sometimes call inert, or it's stable. They're part of the noble gas family. Like the word noble kind of stands out, right? It's like great. It's amazing. So these are the noble gas superheroes of the periodic table. They're the ones that don't need to intermingle with any of the other atoms. You know, there was a saying by the guy that used to work with Warren Buffett, you know, the Oracle of Omaha, the guy that was really good at trading stocks. And his right-hand man said the whole reason you become rich is so you don't have to hang out with people you don't want to hang out with, and you don't have to work with people you don't want to work with. And as you get older, you'll find out that that's very true. So the noble gases have kind of made it. They don't need to hang out with any of the other elements on the periodic table of elements. They're stable on their own. They're not dependent on anybody else to be stable. But most of the rest of these guys are going to have to either work with each other, steal from each other, borrow from each other, or share with each other in order to achieve the stability that the noble gases have. So for example, if you look at fluorine, fluorine's pretty close to neon, but it's not quite there. So if I draw fluorine next to neon, fluorine, let's forget about the neutron number right now. I don't want to keep drawing neutrons because it's not necessary for this discussion. Protons are important to us, electrons are important to us, but for this discussion, neutrons aren't important to us. So if I look at the nucleus of fluorine, it's going to have 1, 2, 3, 4, 5, 6, 7, 8, 9 protons. That's what you have to be fluorine, right? So it's got 1, 2, 3, 4, 5, 6, 7, 8, 9 positively charged subatomic particles, okay? If I add the electrons around that in its elemental form, I see F, fluorine. I don't see F plus and I don't see F minus. So that means I'm also going to have 9 electrons, right? I'll have eventually, so let's just say electron. down here, I'll have 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so the same number of protons and electrons. So when I start adding those based off the octet rule, my first shell, if I'm assigning 9 electrons, holds up to 2. So I put 1, 2 right there. Right. So that one cancels and that one cancels. My next one, how many do I had left? Well, I had 9 to begin with. I added 2 in my first shell. So that means I have 7 left. So that means I have 7 I can assign to the second shell. 1, 2, 3, 4, 5, 6, 7. Okay. So we got to keep 9 protons in the nucleus. That's just a rule if you want to maintain as fluorine. I had 2 electrons in my first shell, which filled it up and made it happy. I had 7 electrons in my second shell, which kind of got it close to full, but we're not quite there. I could have added 1 more. And based off the octet rule, I want 8 in my second shell if I can get it, right? Or at least I want my valence shell, which in this case is the second shell, to be full, right? So the first shell holds up to 2. That one's full. So we had to add another shell. This one holds up to 8. I have 7 in there. So is it full? No. Therefore, we have not fulfilled our octet. Our valence shell is not full. So what fluorine will do is he will grab an electron from somebody else. He'll steal an electron and add it to his valence shell. But because I have gained an electron and I can't change my proton number, these would have all canceled out. But because I gained 1 extra electron here, that means I have to now call it F minus. So we have just formed what's called an anion. We've gained an electron, therefore it has a negative charge to it. Okay. So again, we don't want to keep doing this over and over and over again. I'm sure you can watch a ton of YouTube videos that'll show you ionization if you want to. But what I've done is I've kind of skipped ahead and I'm showing you why we end up forming things called ions. I'll come back in just a minute to cover some of that other information. But what is an ion? An ion is something that has gained or lost an electron. And because it gained or lost an electron, that created a charge on that atom, right? So if I gain an electron, that's going to make me more negative because electrons have a negative charge. If I lose an electron, it's going to make me more positive because I'm getting rid of a negative, right? And again, it's kind of like a proton to electron ratio here. Like how many protons do I have in relationship to the electrons? So what's an ion? It's an atom that has gained or lost an electron and it has acquired a charge. That's what you need to memorize for the test, right? So if you end up having a positive charge, you become what's called a cation. If you end up having a negative charge, you end up becoming an anion. And a lot of times on the periodic table, you can predict what's going to happen. So for example, let me minimize this. There we go. If I go back to the periodic table, this row or this column, sorry, I didn't mean to say row, this column and this column will tend to form cations. They tend to want to lose electrons to become more stable because that means lithium will end up becoming more like helium, sodium ends up becoming more like neon, potassium ends up becoming more like argon in its electron arrangement. So these end up losing electrons to become more stable. So they end up becoming positive. So you get like H plus, Li plus, Ni plus, K plus, right? And these are ones that we talk about a lot in anatomy and physiology, right? So let me show you sodium real fast, why it does that. All right, let me show you sodium, why it does that. So sodium has an atomic number of 11. It has the atomic weight of 23, or atomic mass, if you want to call it that. So 22.99. In its elemental form, it's also going to have 11 electrons because it's Na. It's not Na plus and it's not Na minus yet. Okay. But let me draw out the protons in sodium. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, each of which would have a positive charge, right? So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. And then when I draw the electrons in its normal elemental form, because I don't see a plus or a minus here, we assume they're the same number, right? So there's the same number of electrons, 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. All right, so I can fit 2 of those electrons in the first shell. I can fit 8 of those in the second shell. That's nice because this one's full. This one's about to be full. But I still got 1 extra electron, right? So that means I have to add another shell or orbital because the octet rule says the first shell can hold up to 2, and we had 2 in there. So the second shell could hold up to 8, and we already had 8 in there, so it's full. So since I have 11 electrons in normal sodium, elemental sodium, I have to add another whole shell, and this becomes the valence shell, which has 1 electron in it. So this valence shell now has 1 electron in it. But is it full? Shit, no, it's not full. We're nowhere close to full, right? We would have to get 7 more electrons to make that thing full, and that just ain't going to happen. So the easiest thing to do to make sure I have a full valence shell is just to get rid of this shell altogether. So what we're going to do is we're going to kick that electron out. It's going to take its negative charge with it. So imagine this is gone. So now this cancels, 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 cancels. But this one doesn't have an electron to cancel it anymore. So it becomes Na plus. So when you lose an electron, you become more positive because the proton number didn't change. Okay. And again, if you're not following along with me, that's fine. Just remember, cations are positively charged ions. The T in cation can remind you of that. And it's because you lose or you've lost electrons. Anions, that's what kind of fluorine and chlorine are. Anions are negatively charged ions, and it's because they have gained an electron. Right? Sorry about that. E minus is, again, just shorthand for electron. So in the periodic chart, we can kind of predict which ones are going to be cations and which ones are going to be anions when they ionize, just based off their position. So things like hydrogen, lithium, sodium, potassium, rubidium, these will all form cations. This will lose an electron to become more like helium. This one loses an electron to become more like neon. This one loses an electron to become more like argon. This loses these guys lose 2 electrons. So we end up seeing like Mg++ when we see magnesium floating around in the body. When we see calcium floating around in the body, it's Ca++ because you've lost 2 electrons. But when we see things like chlorine floating around in the body, it's Cl- because it's gained an electron to be more like argon. So again, let's not get any deeper into it than that, but that's why they do what they do. So specifically these columns, these will very easily ionize, right? So whenever you take ions, things that have a charge to them, and you put 2 ions near each other that have opposing electrostatic charges, like for example, sorry about that. If you have, say, Na+, which has a positive electrostatic charge, and Cl-, which has a negative electrostatic charge, these will attract each other. So you end up getting NaCl, which is table salt, and this is an ionically bound substance, right? So what are ionically bound substances? It's when 2 ions have come together and formed a chemical bond amongst each other because they had opposing electrical or electrostatic charges, right? So this ends up forming an ionic bond. You know, what happened to sodium to make it positive? It lost an electron. What happened to chlorine to make it negative? It gained an electron. So chlorine became what's called chloride. These kind of change names when they gain an electron. Don't worry about that. But that's why you sometimes hear the word chlorine. Sometimes you hear the word chloride. Similarly, fluorine becomes fluoride when it gains an electron. Bromine becomes bromide. But these are examples of ionically bound substances. So when you form ionically bound substances, it's ions that got together because they had opposing charges. So you could get lithium chloride, you could get lithium bromide, right? You could get calcium chloride, right? Those form ionic bonds with each other. But not all bonds that form are ionic bonds. Sometimes we end up having bonds that form that are what's called covalent bonds. So while we're talking about ions and ionic bonding, hold on, I'll come back to that in just a second. You can also have what's called covalent bonding, in which you share electrons. So that's the key word. And that's all I really want to say about it, is they share electrons. Good examples of things that go through covalent bonding are hydrocarbons. Like hydrocarbons are very prevalent substances, and they're very important substances. It's part of our diet. You know, carbohydrates have carbon, hydrogen, and oxygen. But hydrocarbons, the simplest versions of those, just have carbons and they're surrounded by hydrogens. And these don't ionize to do this, they just share their electrons. So you sometimes see these little dashes in there, and that indicates that you're sharing 2 electrons, sharing 2 electrons, sharing 2 electrons. So when I look around this carbon, I have 2, 4, 6, 8 electrons because each dash equals 2 electrons, but they're being shared. So this is an example of a covalently bound compound because I have more than one element represented and they're sharing their electrons. That's what these little dashes are kind of telling me. So this is a covalently bound compound. Covalent, you're sharing electrons. That's what you need to know for the test. Which type of bonds share electrons? Covalent bonds. Which type of bonds form because atoms have gained or lost electrons? Ionic bonds. Other things that might describe this, we could say this is organic as well. All hydrocarbons are organic in nature because organic means you have carbon and hydrogen in the substance, right? So again, glucose has hydrogens attached to these carbons, and they also have oxygens attached. I don't want to keep putting all the different things that are on there. It'll get too messy. But these also have hydrogens attached to the carbons, and they have oxygens as well. So these are organic. So anything that has carbon and hydrogen is also organic. I'm trying to think. I'll show you some other words later that might pop up. But for right now, ionic bonds form amongst atoms that have opposite charges or atoms that have gained or lost electrons. Covalent forms amongst atoms that are sharing their electrons. If you ever get asked what's the strongest type of bond, ionic. The second strongest is covalent, right? So ionic is the strongest type of bond. It would be the hardest one to pull apart if we were just using physical force. So if I try to grab a sodium atom with my hand and I try to grab a chlorine atom with my hand and I just try to pull them apart with physical force, it's really hard to get them apart because ionic bonds are really strong. But eventually we're going to talk about how water can break ionic bonds. That's one thing that's really nice about water, is it has the ability to break ionically bound compounds. With radioactive isotopes, this is kind of going back. I really wanted to put a lot of emphasis toward ions because we talk about those the most. But isotope was the other I word that I told you to be careful of. And this is where you sometimes have a different number of neutrons than expected. So sometimes when the neutron number changes and they form isotopes, the atom can become unstable and it tends to fall apart. And when atoms fall apart, that releases a lot of energy, right? So sometimes we end up with these things called radioactive isotopes, where atoms are falling apart, releasing subatomic particles and the energy that holds those things together. And again, that's what forms radiation. And there's different levels of energy associated with radiation, like alpha radiation, beta, gamma rays or gamma radiation, kind of going up in power. Like alpha is fairly weak level radiation. Gamma is very strong level of radiation. So this is the strongest form of atomic radiation. X-rays are artificial gamma rays. So gamma radiation is the strongest form. When you look at periodic table of elements, basically everything on the periodic table is in our body in some quantity. Even arsenic is in our body. But the things that we have the most of are called bulk elements. And I think I wrote those on the board for you the other day. Things like carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. Those make up about 95 to 96% of the body. And the first 4 make up the vast majority. So carbon, hydrogen, oxygen, and nitrogen make up the vast majority of your body. Add phosphorus and sulfur, and you got 95 to 96% of the body by weight. So those are called bulk elements. Things that we don't need in nearly as high amounts, but we still need a fairly significant amount of them, are trace elements. So these might be things you would see on the back of like a vitamin and mineral bottle representing the minerals, right? So again, you can see them on the periodic table, things like copper, fluorine, iodine, iron, zinc. These things we do need in measurable amounts. So oftentimes there's maybe a recommended daily allowance, or there's a certain amount you'd want to get over a certain number of days or weeks. So those are trace elements, but you don't need it nearly as much as you do the bulk elements. And then ultra trace are things that we need in very, very small quantities. And if you get too much, it becomes toxic. So things, again, like arsenic would be that. And most of our acquiring the bulk elements comes from our foods that we eat. So that's where the macromolecules come in. So carbohydrates, fats, proteins, and nucleic acids, those make up the bulk elements, right? So we eat those all the time. This just goes over the octet rule and talks about when you're assigning electrons to the shells or orbitals, how many you can put in each shell. So 2, 8, and 8 is how we remember it. When you get into Lewis structures and Lewis dot diagrams, that helps you, I guess, formulate or figure out how covalent bonds might occur. You don't need to know this for the test. I'm not going to discuss it. You don't need to know any of this for the test. This is something you would do more in a general chemistry class, but it kind of helps you understand how covalent bonds form. This is an example of a covalently bound methanol molecule. It's also a compound, right? So this is one molecule of methanol. Methanol sometimes is called wood alcohol. Certainly not something you'd want to drink. Just showing you ionization of sodium and chloride. Sodium tends to give up an electron, which makes it positive. Chlorine tends to gain an electron, which makes it negative. And then when they have these opposite charges, they're attracted to each other. So they end up forming sodium chloride. Water, again, we can discuss many different ways. Water is one of the more plentiful substances in the body. About 55% of the body is water. It's very useful for transport. It's also a very good solvent. We talked about that in chapter 1. Some of the things we've mentioned so far in chapter 2 about water is it's a compound because we have more than one element being represented here. So we have 2 hydrogen atoms and 1 oxygen atom. You can also say it's covalently bound because we're sharing these 2 electrons right here. So I see that little line here and that little line there. But one other thing that we want to mention is water is also polar. It has polarity. So when you look at a water molecule, water molecules end up having some extra electrons up here, which are pretty negative. When you form your bonds with the hydrogen ions, there ends up being a partial negative and a partial positive charge here. Like it holds the electrons in that bond tighter toward the oxygen than it does the hydrogens. Ignore that, those little dots for right now. But what that means is your oxygen end of a water molecule tends to be negative in nature. The hydrogen ends of your water molecule tend to be positive. So that ends up giving it polarity, right? So imagine I have a magnet with a negative pole and a positive pole. Water has polarity. Right? So the definition of polarity is kind of weird. It says where we have a disproportionate number of electrons on one side of a molecule versus another. Electrons, again, carry a negative charge with them. So if I have more negative charges on one side of the molecule than I do the other side is relatively positive, right? So one side of the molecule is more negative than the other. So that's polarity. The easier way of thinking about it is you have a positive side and a negative side. We already discussed organic. So organic molecules or compounds are carbon containing, and they also have hydrogen. Inorganic is most of the periodic table. You know, most of the periodic table is not carbon or carbon compounds. Hydrogen bonds, these are fairly weak bonds. Like if you're trying to list out like bond strength, like bond strength, ionic bonds are your strongest type of bond. So bond strength. If I'm trying to hold atoms together, what's the strongest type of bond that I can form? Ionic. What's the second strongest type of bond I can form? Covalent. What's the third strongest type I can form? Hydrogen. And then the last one's called van der Waals forces, and I can never remember how to spell these things. So van der Waals forces. And those are the weakest. So that's the type of question that comes up with bond strength. What's the strongest? Usually ionic, second strongest covalent, third strongest is hydrogen. So chemical reactions, it's when we form or break bonds amongst atoms, ions, or molecules. Reactants are things that go into a chemical reaction. Products are things that come out of a chemical reaction. And I'll show you simple examples of that in just a second. For example, two very simple types of chemical reactions we talk about are things called synthesis reactions and things called decomposition reactions. The arrow will tell you where the reactants are in this reaction and where the products are. The arrow always points toward the products. So if I'm taking smaller substance A, combining it with smaller substance B, and that yields a larger substance AB, where a bond has formed between those two things, that's called a synthesis type reaction, in which these are the reactants and this is the product. So the arrow points toward the product. But similarly, if you started off with something larger and the chemical reaction caused it to fall apart, that's called a decomposition reaction. So in this case, this is the reactant and these are the products. So really, it just depends on which direction the arrow is facing. That'll tell you where the reactants are versus the products, because the arrow always faces toward the products. Synthesis reactions build things up. Decomposition reactions tear things apart. Okay, so chemistry can go in either direction. Similarly, we mentioned that same concept when we talked about anabolism and catabolism. So synthesis is similar to anabolic processes if you're dealing with living organisms. Decomposition is similar to catabolic processes. So in this case, it's just the context is different. This is general chemistry. We use the word synthesis and decomposition. In living organisms, we might say anabolism versus catabolism. But the words are somewhat interchangeable. One reaction that we do a lot in our body is a combustion reaction, and we can also call it a redox reaction when we get into chapter 4, where we burn sugar as a fuel source. No different than burning gasoline in your car. It's the same type of reaction. It's called a combustion reaction. So combustion reaction. And again, the most common form of combustion reaction we run in our body is when you take glucose. One molecule of glucose is made up of 6 carbon atoms with 12 hydrogen atoms and 6 oxygen atoms. That's one molecule of glucose. So this is glucose. You combine that with 6 molecules of the oxygen that we breathe, and that's going to end up yielding 6 molecules of carbon dioxide plus 6 molecules of water plus energy. And this is the main way our body makes energy. And the main form of energy we're trying to make is what's called ATP. Adenosine triphosphate is what that stands for. It's a type of cellular energy. All right. And this also gives off heat as well. It's also how we generate body heat, or thermogenesis. So how do we form most of the energy in the body? By burning sugar in the presence of oxygen. So this gets lots of names depending on what chapter you're in. In chapter 4, this is called the complete aerobic respiration of glucose. In this chapter, this is called a combustion reaction. Because combustion reactions are whenever you take some type of organic molecule, this has carbon and hydrogen in it, so it's organic. You combine that with oxygen, and then you end up getting carbon dioxide plus water plus energy. And it's the energy that we want, right, from a combustion reaction. Just trust me, that said energy at one time. But this is the same reaction you run in your car. You just change the fuel. Like you put octane plus oxygen gives carbon dioxide plus water plus energy. Or you can burn wood in a fireplace. Wood plus oxygen gives carbon dioxide plus water plus energy. Right? And sometimes the type of energy might appear different. Like if I'm burning wood in a fireplace, I'm going to get heat and light. If I'm burning fuel in a car, I'm going to get mechanical energy, right, and heat. But again, this is the same reaction that we use to make energy when you're burning fossil fuels. Right? Let's see, what else do we have here? Catalyst and enzymes. I'm just going to tell you what these are, so you can write them down when you're listening to this video. A catalyst is anything that speeds up a chemical reaction, but it's not used up or altered by the reaction. So a lot of times, catalyst can be used over and over and over again. It might just be the presence of a particular type of substance. Like, for example, when I'm trying to burn octane in a car, we might not be able to do that efficiently fast enough by the time it makes it to the muffler if we don't end up adding a catalyst somewhere along the way, like platinum or palladium. So when you burn octane in a car, you need oxygen to do that. So you have an air intake and you're burning the fuel. You'll usually catalyze that two different ways. I'll add a spark plug. The spark will kind of ignite the reaction, get it going faster. And then platinum and palladium will help accelerate the formation of the byproducts. So it ends up being another type of catalyst. So in that case, there's two catalysts, a spark plug that ignites the reaction and the presence of platinum or palladium, which helps to finish the reaction faster. So there's two catalysts that we use inside of a car. But a catalyst is anything that speeds up a chemical reaction, but it's not used up or altered by the reaction. An enzyme is a specific type of catalyst that is formed from a protein. So an enzyme is a protein catalyst, is what we usually call it. So in our body, we use a mixture of different types of catalyst and enzymes to run our chemical reactions. So that way we can run them at the right speed. And one of the most common forms of catalyst that we have in all chemical reactions is heat, the presence or absence of heat. Generally, the more heat you add, the faster a reaction will run. That's why we heat stuff up when we cook it. It makes it mix together faster, or it makes the chemical reaction take place faster. So in our body, our chemical reactions run best about 98.6 degrees. That's the optimal rate of our chemical reactions. So that heat is catalyzing our chemical reactions, but we also use enzymes. Enzymes might get the reaction going, but enzymes are protein catalysts. If you want to think about the opposite of that, though, how could I slow down chemical reactions? Well, let's remove heat, right? If I want to slow down a chemical reaction, take heat away. So refrigerators do that for us, and freezers do that for us. So if you want to slow down, say, decomposition of food, stick it in a refrigerator because there's less heat there, so it's not going to spoil as fast, right? We're slowing down decomposition. Or if I really want to slow it down, stick it in the freezer, because then it's really slowed down decomposition. And then the last topic we really talk about for chemistry is acid-base chemistry. I think I can do most of this on paper. The definitions are all here. Again, we're going to try to keep this as simple as humanly possible. I'm going to give you a little trick to understand how pH works, just in case it ever comes up on a standardized test. And we'll probably have a similar question on our test. But one thing to point out here, because I might forget to mention this when I am going over acid base on paper, anytime you mix together an acid and a base, you're always going to get a water and a salt. But nothing's really built up and nothing's really torn down. So it ends up being called an exchange reaction, where you basically just switch partners. So for example, hydrochloric acid, when you mix that with sodium hydroxide, you end up getting water plus a salt, right? And if you want to, ask me what a salt is when we get back, and I'll show you on a periodic table. But a salt is anytime you have a metal and a non-metal. But in this case, this hydrogen ended up moving positions, I guess you could say, and this sodium ended up moving positions. And so what ends up happening is the hydrogen jumped over here with the OH, and this sodium jumped over here with a Cl, right? So they didn't really make anything bigger. They didn't really make anything smaller. They just switched partners. So the hydrogen changed positions with the sodium changed positions with the hydrogen, and you ended up getting NaCl and HOH, which is the same thing as saying H2O, right? So that ended up giving us water plus salt. So when you mix an acid and a base, you always get a water and a salt. That's just an example of what's called an exchange reaction. But let me do, I think, the rest on paper, and that'll, again, I'll talk about the basic definition of acid and base. We will end up talking about pH and what that's measuring, what our normal pH is supposed to be. Acidosis versus alkalosis, I'll do that for you. And in order for us to maintain proper pH in the body, we use lungs and kidneys. So part of the respiratory system and the urinary system help us do that, just in case I forget that. And that should take us toward the end. Okay. So the last thing I want to talk about is acids and base, or acid-base chemistry. Starts here on this slide. And I'm just going to do it on paper. So when you get into acids, the way I want you to remember it is acids are anything that has the ability to give up or donate hydrogen ion to solution. It adds hydrogen to a solution. So for example, if I were to take hydrogen chloride, which is one of the more famous types of acid, and I stick it in a glass of water, because water is polar, has a negative oxygen end and these positive hydrogen ends, water is actually able to pull hydrogen chloride apart, right? And it goes through a process called dissociation. So this falls apart when it gets into the water. So that ends up giving me a H plus and a Cl minus because they were ionically bound, right? So now that hydrogen chloride has been added to the water, I just increased the number of hydrogen ions floating around in that water. So I just donated a hydrogen ion to solution. So now this is called hydrochloric acid. So acids have the ability to donate hydrogen ions to solution, right? If I were to add, let's see, H2CO3 to water, don't worry about what that is. It'll give up a hydrogen ion plus a bicarbonate ion. So an H plus and an HCO3 minus. Don't worry about this. Did I just add another hydrogen ion to that solution? Yes, therefore that's an acid. So an acid is anything that has the ability to increase the number of hydrogen ions in solution, or you could say donates hydrogen ions to solution, okay? But a base is the opposite. A base is something that has the ability to receive or pull hydrogen ions from solution. Or it can pull it out of solution or bind to it, removing it from the solution. So if I already have a solution that has hydrogen ions floating around in there, and let's say I add sodium hydroxide, which is a very common industrial base, again, this is going to fall apart in water. So that's going to give you an Na plus and an OH minus. That H plus and that OH minus will get together and they form water. And when that happens, it just disappears in the solution because this was water already, right? So again, you had a couple of H's floating around. You add sodium hydroxide, which is a base. That's going to give me an Na plus. Don't worry about this. I'm not worried about the Na plus. An OH minus. That OH minus now pulls the hydrogen in. It attaches, and now we have water. And therefore, that hydrogen has been pulled from that solution. So this is a base. If you don't get what I just drew or mentioned, don't worry about it. Just remember the definition. Acids have the ability to donate hydrogen ion to solution. Bases have the ability to receive hydrogen ion from solution. Hydrogen ion, by the way, if you look at the periodic table, I'm not going to bring this back up because it's a lot of slides to click through and I don't want to waste your time. But on the periodic table of elements, hydrogen has the elemental symbol of H. It's the very first thing on the far left top, all right? It's the very first element on the periodic table. It has the atomic number of 1. It has the atomic weight of 1.001. So that really means you only have 1 proton in the nucleus. There's no neutrons. If that was the case, the atomic weight would have been 2. So hydrogen atoms have one proton in the nucleus, no neutrons. But it also usually has one electron in this form. But when that electron is given up, right, all you have left is one proton. That's a hydrogen ion. So a hydrogen ion sometimes gets called a proton. So sometimes when you read acid-base chemistry, they sometimes talk about donating protons or deprotonating something. It's the same as saying a hydrogen ion. And less explanation is sometimes better. When you look at two solutions, let's compare solutions. So again, let's pretend we have a vessel containing water. Here's another vessel containing water. And this one has this many hydrogen ions, and this one has this many hydrogen ions. This is the more acidic solution than this one is. So the more hydrogen ions I have in solution, the more acidic it is. So comparatively, this would be more basic or alkaline. Comparatively, it's relative. So this solution is more basic or alkaline than this solution is, right? It's this one's pH would actually be higher. This one's pH would actually be lower. That's where it gets confusing, but forget about that for a second. If I compare two solutions and this one has more hydrogen ions in that solution, it's more acidic, because remember, the basic definition of an acid is anything that has the ability to donate hydrogen ions to solution. So if this has more hydrogen ions already donated to that solution, it's more acidic. Okay. But when we measure pH, we usually do that on a pH scale, which is a really funky math scale where you have an inverse log, which sucks because you have to hit extra buttons on a calculator. But the pH scale, in simple terms, goes from 1 all the way up to a pH of 14. A lot of times they'll put a pH of 7 as being neutral, right? Because that's where water sits, and water doesn't have any more hydrogens than it does hydroxides. So that's kind of why they put water as neutral. Don't worry about that for right now, because to us, 7 is not neutral. In humans, our neutral is right here, about 7.4. This is neutral for us. So this would actually be too acidic. If I had a pH of 7 in my blood, that's too acidic because I'm going in this direction. Sorry, I didn't mean to leave that off. But again, in most scales where you see a pH, they'll put, and I'll bring this up because that way you can see it. Most scales where they're showing pH, they'll put water in the middle. It's 7, but the more you go in this direction, so I can start, it doesn't matter where I start. The more I go in this direction, the lower the pH, the more acidic it becomes. The more I go in this direction, the higher the pH, the more basic or alkaline it becomes. Okay. So I tend to always draw my scale top to bottom. So I have a pH of 1 down here at the bottom, pH of 14 up here at the top. So now what I'm telling you is when we're measuring pH, think about it as a percentage of hydrogen. How much hydrogen is actually in that solution? And since it's going to be a percentage, you could kind of think about it as a decimal. And what the pH scale does, because it's an inverse log, is it tells me how many spaces away from 0 am I when I'm talking about how much of this solution is just hydrogen. So work with me for a second here. If I take a solution and it has this percent of hydrogen compared to the rest of the solution, 1 out of every 10 parts of that solution is hydrogen. So how many spaces away from 0 am I? 1. This would put me at a pH of 1. So that doesn't seem like it's very much, right? But that's a lot, because a lot of times these things are in water, and it's basically saying 1 out of every 10 molecules floating around in that glass of water is a hydrogen ion. So that would be a lot of hydrogen ions floating around. So that would put me at the lowest position on this pH scale of a pH of 1. And this is very acidic, because the more we head in this direction, the more acidic we become. Everything's relative on this scale. So if I go from a pH of 2 to a pH of 1, this is 10 times more acidic than it was here. So if I'm going from here to there, I just became 10 times more acidic. If I'm going from a pH of 3 to a pH of 1, I'm 10 times 10. I'm 100 times more acidic, because it works like this. A pH of 1, that's the decimal that kind of matches up with how many parts of this solution is made up of hydrogen. 1 out of every 10 parts, or is it 1 out of every 100 parts? Or is it 1 out of every 1,000 parts? Or is it 1 out of every 10,000 parts? Something like that. That's where your pHs are coming from, like a pH of 1, pH of 2, pH of 3, pH of 4. So every time we go down a whole number on the pH scale, it's a factor of 10 how much more acidic it is. So if I'm at a pH of 2, that's 10 times less acidic than a pH of 1. Or if we go from pH of 2 to a pH of 1, I've just become 10 times more acidic, right? So it's kind of measuring how many spaces away from 0 am I. If I'm at a pH of 14, I would be like this. I'd be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, right? So a pH of 14 doesn't have a very high percentage of hydrogen. So again, and everything's relative. So if I start going from, say, a pH of 2 to a pH of 3, sure, compared to water, I'm still on the acid side. But if I go from a pH of 2 to a pH of 3, I just became 10 times more basic or alkaline, right? So again, it's different than you probably were initially taught this. So certainly if I'm comparing it to water, which is a pH of 7, I know these aren't spread out very well, but again, 7's after 4. So, but if I'm at water at a 7 and you look at a pH of 3, what is it? Something with a pH of 3? Yeah, we would consider that acidic compared to water. But if you're comparing a pH of 3 to a pH of 2, this is 10 times more basic or alkaline, because as we go up the scale, we're becoming more alkaline. So as you go down the scale, you're becoming more acidic. As you go up the scale, you're becoming more basic, or what's called alkaline. So in humans, we need to be somewhere between 7.35 to 7.45, right? So ideally, homeostatic wise, we'd like to be about 7.4. But if I start to become 7.3, 7.2, 7.1, 7.0, we're heading down toward 1. That is called acidosis, and that's no good. If I start to go 7.5, 7.6, 7.7, 7.8, we're going up the pH scale. That ends up being called alkalosis. So to prevent that, we use our kidneys and our lungs to help regulate the pH. Okay. And that's really all we needed to cover for test number 1. So real quick overview of where we are and what we've covered. We just did as much chemistry as we need to do for test number 1. Right? Remember, I told you the cutoff point somewhere around in here where it starts talking about macromolecules. So this is just finishing up talking about acids and pH. Okay. This we'll talk about later. But this is the chemistry chapter, chapter 2. So normally if I had been on campus, we would have achieved that over several days. So here is week 2, where Monday is 8:25. I'll be here and we'll finish up chapter 1 probably. Maybe we might get into chapter 2 and you'll get some things redundant, but I'm doing this ahead of time, so I don't know yet. But here's Wednesday of week 2. Here's Friday of week 2. You're just going to be watching the video at home. There's no class on Labor Day. Here, that's when we would have finished chapter 2 in class if I had been there. Usually takes about 3 classes to go over this. So make sure that you have watched the video and you understand everything by here so you can ask questions right here. Okay. And then week 4 on September 8th, Monday, September 8th, that's when we take lecture exam 1 over chapters 1 and 2. So all of chapter 1 and then chapter 2 up to about slide 30-ish. Okay. So I'm going to post this for you in just a little bit. I'm going to explain this in class tomorrow, and I'll explain it again Monday, obviously. But that's it for right now.